I'm Jared Harrington, and today I will be discussing Lab 2 Lines of Charge. So, the objective for this lab was to produce a computational model of two charged tapes exerting an electric force on each other, and then use this model to estimate the amount of charge on each tape necessary to float one above the other. Unlike in Lab 1, this time you must distribute the charge evenly across the length of the tape in your computational model and not concentrate the charge at a single point. So some fundamental physics principles are Coulomb's law, the point charge formula, the line charge formula, gravitational force, Newton's second law, and also the electric force is an important principle in this lab. So going back to lab one, the procedure was to place one piece of tape on a hard surface, then tape another piece of tape on top of it, then rip it off to create a charge, which is the U-tape. Repeat the first step, and then observe the interaction between one U-tape and your hand, one or between two U-tapes, and between a U-tape and the charged plastic pin. Then you will attach a U-tape, which is tape B, to two books. Then you hold another U-tape, which is tape A in this case, under tape B until there is movement in the positive Y direction. Then record your observations and data. So going back to lab one, the system is the suspended tape, and the surroundings is the held tape plus everything else. And here are the data that I gathered. Now moving on to this lab. So using the results from lab one, we can find a new Q. So in this case, in lab one, we were using the point charge formula, but that using that formula only assumes that the charges are concentrated around one point. In this lab, we're focusing on the charges being distributed evenly across, which you would use the line charge formula. And then here are some of the assumptions. So here is a computational model. In this point, here are the initial conditions. And then this is the new Q that you get from setting the electric force equal to the gravitational force. And the electric force, in this case, you would be using the line charge formula instead of the point charge formula to get this result. And then here is the function for the electric field. And then this slide shows the function of the line charge equation. And then this is also a continuation of the line charge function. And then here, this just shows the net electric force and the gravitational force and how to represent that in the next figure. So these are the results from the computational model. As you can see, the yellow and green arrow, both of these represent or the yellow represents the electric force and the green represents the gravitational force. These are not equal, which means that there are some sources of error. That could be from mishandling the U-tapes, inaccurately measuring the separation distance between tape A and tape B, and then having the assumption that the charges of each piece are equal and are distributed equal across the tape, because this is not true in all conditions. So for a what if question, in lab one, Q was equal to 1.167 e to the negative 8 versus in this lab, Q was found to be 2.37 e to the negative 8, which is almost a 50% difference. So the question is, why do these estimates differ? So in lab one, we were using the point charge formula, which is treating all of the charges as if they were concentrated around the single point, which is not accurate. In reality, the charges are all distributed along the length of the object, which the second Q, the new Q, calculates. The line charge model is a better depiction of the accurate distribution of the charges across the tape. So the second value of Q is closer to reality.